Hello everyone. So in the previous chapter on kinematics, after we had defined the engineering strain, we had gone on to ask ourselves the question that suppose we are sitting at a particular point and we know the various components of the strain tensor at that point. Then and given or asked to find the value of the engineering strain along a particular direction, we can very well use the formula that connects the engineering strain to the strain tensor using the unit vector. We can definitely find that value. But we asked ourselves the question that what is that direction along which the engineering strain will be the highest. So sitting at the same point, there will be various directions around it. So which is that direction along which we'll get the highest value of the engineering strain? And the way we proceeded was by discussing within the topic of principal strains how to find that out. And we did that by using a Lagrange multiplier and by doing some kind of derivatives. Now we could proceed in a similar fashion in this chapter also, because today we are going to start discussing principal stresses. So in the context of principal stresses, we'll get to the derivation of the formula or whatever is required a little bit later. But first of all, let us try to formulate it in terms of a physical question, like what we are trying to find out. So in the previous chapter, okay, in the previous chapter on kinematics, we first defined the engineering strain, and then we talked about the maximization of it. In this chapter, what we have just discussed in the previous part of the lecture was the normal and the shear components of traction. And as mentioned near the end of the last lecture, we are going to base our entire discussion of principal stresses on this normal component of the traction. In fact, what we are going to ask is, so let me refer to the slide. So if we refer back to this thing, this particular formula, you see that the normal component of the traction is connected to the stress tensor at a particular point through this n hat. So the question we are asking in this chapter, just like as we had asked in the previous chapter on kinematics, is that what is the direction of n hat which is going to maximize this value of Tn? I repeat, what is that direction of defined by this n hat such that the normal component of the traction vector gets maximized? Now your intuitive feeling may be that we can just proceed exactly like earlier. In fact, the formula is so very similar, like we don't even have to derive this. And it's true, we don't have to derive anything if we were to proceed like that. But we don't want to proceed like that. Rather, we want to take a slightly different approach in order to get a better physical insight of whatever is happening with stresses and tractions. So let us look at this picture. Our question is, what should be the direction of n hat such that the value of this Tn is maximized? Okay, now forget about all the formula, all the matrix representation, everything. Just think geometrically or very physically. When is this Tn going to be maximum? So suppose this T vector were having a smaller angle compared to what is shown here. Suppose it was oriented like that. So the contribution of the T vector to this Tn would be a little bit higher. So in the extreme limit that the T vector happens to be parallel to this n hat, happens to be, okay. So in general, the traction vector is never going to be parallel to the n hat. But in the very, very special scenario that the traction vector is parallel to the n hat, then we can say that the entire Tn that will capture the strength of this traction vector, and there will be no shear component of the traction left. It is in that situation, it is for such a plane where the n hat is such that the traction vector is parallel to the n hat, it is such a plane is referred to as the principal plane, and the stresses associated with it are referred to as the principal stresses. Okay, so instead of going by the route of Lagrange multiplier and all the derivatives using the index notation which we had done in the previous chapter on kinematics, we are going to take a more geometrical approach, and we are going to say that let us take a traction vector such that it is parallel to the n hat. Okay, so this is our strategy now. So for principal stresses, what we are going to say is this. First of all, we say that the n hat that is given by n1 e1 hat plus n2 e2 hat plus n3 e3 hat, where e1, e2 and e3 are respectively the unit vectors along the three coordinate axes. So just referring to the previous figure, the e1 is along this x1, the e2 is along this one, and e3 is along this one. The unit vectors along the three coordinate axes. And n1, n2 and n3, they are the components of the unit of this unit vector n hat. Now what we are saying is that the t vector should be parallel, or let me write it in words, for Tn to be maximum. We must have t vector parallel to n hat. So that means the t vector will be a certain magnitude, its magnitude multiplied by the n hat. And what is that magnitude? We understand that the entire magnitude will be captured by this Tn. So this is a very, very important step to write. So it will be like this. Okay, the entire magnitude of the t vector is captured by the normal component itself, because we know by definition that the normal component of the traction vector is the component of the t vector along the n hat. But in this special scenario, the t vector itself is parallel to the n hat. So the Tn is the whole magnitude of t vector. Okay. So that means if we expand it out a little bit, it will be Tn n1 e1 hat plus Tn n2 e2 hat plus Tn n3 e3 hat. Alright. So this is one way of representing it. However, we could have also represented it in another fashion, and that would be by using the Cauchy's formula. But before we do that, what we'll do is we will write this entire equation, which is this equation, which is basically a vector equation in terms of components. So it's very easy, but we'll still do it for the sake of completeness. So it will be Tn n1, T2 will be Tn n2, and T3 will be equal to Tn n3. That's very easy. Next, what we are going to say is we are going to use so let me go to the next slide. We are going to use this particular formula, which is the Cauchy's formula. Okay, so that means we have already written this earlier, so I'm not going to discuss this in too much detail. So I'm just writing down the components. And of course, I'm utilizing all throughout the symmetricity of the stress tensor. Now you see, suppose I go back and name these equations #1, #2 and #3, and these as *1, *2 and *3. So what I will do is I will subtract all the three star equations, or rather all the three hash equations from all the three star equations, and that will give me what? You see, if I do *1 minus #1 here, what will I get? On the left hand side I have T1, here also I have T1. So this is going to give me 0 is equal to ∑11 minus Tn, N1 plus ∑12 N2, because you note here I have no contribution from N2 and N3. So this is what I obtain. Next, ∑12 N1 plus ∑22 minus Tn N2, because you note that in #2 all that I have is a coefficient sitting with this N2, so that contributes here, and then ∑23 N3, and finally I have ∑13 N1 plus ∑23 N2 plus ∑33. As you can expect, this is going to be minus Tn N3. Alright. Now, usually when you are setting up the framework for finding the principal stresses, what we say is that the very special circumstance or situation where the traction vector is parallel to the n hat, the normal component which we have written here, this normal component is usually given by the simple sigma itself. Okay, this is just the simple sigma. This Tn, instead of this Tn, we just write this as the sigma. So if we do that, then we can quickly change our notation here. To sigma, sigma and sigma, and if we go back to this thing also, we can change it to sigma, 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 just a change of notation. Now the moment we have these things, you can understand that this can very well be set up in a matrix form. So because each of these equations have the n1, n2 and n3, which you note are the scalar components of the unit vector of concern. So we can set it up like sigma 1 1 minus sigma 1 2, sigma 1 3, sigma 1 2, sigma 2 2 minus sigma 2 3, sigma 1 3, sigma 2 3, sigma 3 3 minus sigma. This is written as a 3 by 3 matrix, and that is multiplied with n1, n2, n3, and that is equal to the 0 column vector. So we can write this as 0 0 0. You understand that the way that I have written it here, this is exactly equal to what is present here in the form of 3 separate equations. Alright, so this is basically the framework which you have come across earlier in the previous chapter of kinematics, and this is the very familiar form of an eigenvalue problem. So in order that you have non-trivial solutions, for non-trivial solutions, what we must have is that the determinant of this matrix, the determinant of that matrix must be equal to 0. All right. So if we expand this out, if we actually carry out the algebra of finding this determinant, what we'll find is this can actually be written. So I'm going to the next slide here. It can actually be written in a very nice and clean form like this: sigma cube minus I1 sigma square plus I2 sigma minus I3 is equal to 0, where I1 happens to be just sigma 1 1 plus sigma 2 2 plus sigma 3 3. I2 is a very nice symmetric form which can be expressed in a very neat and clean fashion like this. And finally, I3 is nothing but the entire determinant of the original stress tensor itself. Okay, so in case you're a little bit surprised by this I2, please note that if you just expand it out, it will be like sigma 1 1 sigma 2 2 minus sigma 1 2 square plus sigma 2 2 sigma 3 3 minus sigma 2 3 square plus sigma 3 3 sigma 1 1 minus sigma 1 3 square. Because it comes out in that form, it can be conveniently represented in a more visually appealing form like this. Similarly for the I3. Okay, now what is so special about this? Or is there anything special about this? We must ask ourselves this question, because it has come out in such a neat and clean form. Is there something special going on? Actually, yes. Because let's go back to the original figure from our previous lecture here. You see we had started our discussion by specializing to a particular plane on which we want our n hat to be parallel to this traction vector. But other than that, there is nothing special about that plane, meaning that it is not that this n hat necessarily has to be along the x1 or x2 or x3. You must understand that. Now, suppose we let me highlight this again. What I'm trying to achieve here, I'm trying to give you a special reason or motivation or justification for these particular coefficients to come out in the form that they have. Okay, because it is so neat and clean, I want to highlight that there is indeed something special going on, and that is why I want to have this discussion. So we understand that in general the n hat is not going to be along the x1, x2, x3. That much is okay. However, we are concerned about a single point here. Okay, and we have drawn this plane like this. Okay, and we are drawing the various vectors and we are writing out the various components of the vectors, the t1, the t2, t3, the various things. In fact, the various stress components, the sigma 1 1, sigma 2 2, sigma 3 3, and the rest of them, sigma 1 2, sigma 2 3, sigma 3 1. But whenever we are writing out all those components, please note that they are very specifically referred to this particular choice of the coordinate axis. Suppose instead of this x1, x2, x3, suppose we had chosen a different orientation. Suppose we had taken some kind of x1 dash, x2 dash, and x3 dash. Please note that I am not changing the plane itself. The plane, the physical plane remains as it is oriented. Okay, so, but what I am doing now is I am considering a different orientation of my coordinate axis, my reference coordinate axis. That is completely under my wish. I can change it as I feel like. So I'm changing it. The moment I change it, the original vectors, the physical meaning of those vectors, they do not change. However, the mathematical representation as far as the various scalar components, the t1, t2, t3, the n1, n2, n3, they are going to change. Okay. Now, this is very important. No matter what choice of the coordinate axis I choose here, okay, whatever orientation of the coordinate axis I may choose here, can it ever change the fact that there will be a certain plane on which the special thing about this thing being parallel to this is going on? What I mean is, if you are choosing, if you have managed to find out such a plane where the traction vector, the actual physical traction vector is parallel to the unit outward normal, would it ever depend on the choice of your reference axis? No matter what axis you may choose, no matter what scalar components they may be represented by, but the physical truth that the traction vector is parallel to the unit outward normal to the plane, that fact is not going to change. Okay, this is an invariant truth of nature that is not going to change. The traction vector being parallel to the unit outward normal to a certain plane, that is a physical truth. The mathematical representation involving the various components may change with different choices of the coordinate axis, because that is just a mathematical representation, but the physical truth remains invariant. And that is what is specially going on here. Let us come back to this thing, this final thing that we have found out. You see, even though this I1 involves the sigma 1 1, sigma 2 2, and sigma 3 3, and as I have told you, if I had chosen a different set of coordinate axes, I would obtain different values of this sigma 1 1, sigma 2 2, and sigma. Maybe they would be called sigma 1 1 dash and sigma 2 2 dash and sigma 3 3 dash. The dash representing the different choice of the coordinate axis. Similarly, these values, the sigma 1 2 dash would come up here, the sigma 2 3 dash would come up here, and the sigma 1 3 dash would come up here. But if you go back to this equation, okay, these are the equations which are telling you the values of these sigmas. What are these sigmas? These sigmas are actually the Tn, the normal component of the traction vector. That is the physical truth as regards its maximum value. And we have already said that that physical truth cannot change. So we must conclude only one thing. There is only one thing to conclude here, which is that even if the individual values of these various stress components may change, but the way that they are combined to form I1, that the way that they are combined to form I2, and the way that these are combined to form the I3, that cannot change. So no matter which coordinate axis you choose, the I1 value is going to be invariant, the I2 value is going to be invariant, the I3 value is going to be invariant. That is an extremely important point, which is going to help you all throughout your life as far as your engineering practice is concerned. Please understand the connection with this mathematical equation. This is an equation, it is a cubic equation, it is going to have 3 roots in general. Those 3 roots will give you 3 possible values of the normal component of the traction vector. Now, if you take different axes, that is just a reference choice for you, that physical truth cannot change, and that is why the values of I1 and I2 and I3 cannot change. Okay, it simply cannot change, the I1, I2 and I3. So even though these individual values may change, but the way that they are combined, it is not going to change. So it's something like this. Suppose in one coordinate axis your sigma 11 turns out to be 1, sigma 22 turns out to be 2, and sigma 33 turns out to be 3. So all in all you have I1 is equal to 6. Okay, with the correct units, of course, maybe like in terms of megapascals or something like that. But in another coordinate axis, this sigma 11 value can have the value 2, the sigma 22 value can again have the value 2, and maybe sigma 33 also has the value 2. But they will always be like this, that their total sum has to be equal to 6. Okay, again you choose another one, maybe it comes out to be 1.5, it comes out to be 3.5, so that is 5, and the sigma 33 has to be equal to 1, so that the total is equal to 6. In a similar fashion, your sigma 12 can have different values in different coordinate axes, sigma 23, sigma 13, but the particular way that they are combined, okay, this is almost like magic. The way that they are combined, that is an invariant value given by this I2. So that invariance thing is actually represented by the I2. Here also, this determinant value is an invariant I3. So no matter which coordinate axis you choose, the roots are always going to be the same, meaning that the normal component of the traction vector is always going to be the same no matter what axis you are referring to. And this is one of the most important lessons, perhaps the most important lesson that you can obtain from this chapter. Alright, so we'll continue with our discussion of principal stresses and how we can build on that to represent other things. So we'll stop here for today. Thank you very much.